In continuation to the previous lecture, today we will study 4 distinct zones of the atmosphere. This figure shows above the stratosphere the temperature diminishes again, creating the mesosphere or middle layer. The thermosphere or heated layer begins at about 50 km. This is a region of highly ionized electrically charged gases, heated by a steady flow of high energy solar and cosmic radiations. In the lower part of thermosphere, intense pulses of high energy radiation cause electrically charged particles to glow. Thus, in the lowest 10 to 12 km, the layer known as troposphere, the air moves ceaselessly, flowing and continuously redistributing heat above the stratosphere. The temperature diminishes again, creating the mesosphere or middle layer. The thermosphere or heated layer begins at about 50 km. This is a region of highly ionized, electrically charged gases heated by a steady flow of high energy solar and cosmic radiations. In the lower part of the thermosphere, intense pulses of high energy radiation cause electrically charged particles to glow. Thus, in the lowest 10 to 12 km, the layer known as troposphere, the air moves ceaselessly, flowing and swirling and continuously redistributing heat and moisture from one part of the globe to another. The composition and behavior of the troposphere and other layer control are weather, temperature and moisture condition in a place and other climate long-term weather patterns. The sun supplies the earth with the enormous amount of energy, but that energy is not evenly distributed over the globe. Incoming solar radiation in solution is much stronger near the equator than at the altitudes. Of the solar energy that reaches the outer atmosphere, about 1/4 is reflected by clouds and atmospheric gases, and another quarter is absorbed by carbon dioxide, water vapor, ozone, methane, and a few other gases. This energy absorption warms the atmosphere slightly. About half of incoming solar radiation in solution reaches the Earth's surface. Most of this energy is in the form of light or infrared energy. Some of this energy is reflected by bright surfaces such as snow, ice, and sand. The rest is absorbed by the Earth's surface and by water. Surfaces that reflect energy have a high albedo. Albedo means reflectivity. Most of these surfaces appear bright to us because they reflect light as well as other form of radioactive energy. Surfaces that absorb energy have a low albedo and generally appear dark. Black soil and dark green vegetation, for example, have low albedos. Absorbed energy heats the absorbing surface, evaporate water, or provide the energy for photosynthesis in plants. The second law of thermodynamics, absorbed energy is gradually re-emitted as lower quality heat energy. A brick building, for example, absorbs energy in the form of heat. The change in energy quality is very important because the atmosphere selectively absorbs longer wavelengths. Most solar energy comes in the form of intense, high energy light or near infrared wavelengths. This short wavelength energy passes relatively easily through the atmosphere to reach the Earth's surface. Re-emitted energy from the Earth's surface is lower intensity, longer wavelength energy in the far infrared part of the spectrum. Atmospheric gases, especially carbon dioxide and water vapor, block much of this long wavelength energy, holding it in the lower atmosphere and letting it leak out to space only slowly. This re-emitted or terrestrial energy provides most of the heat in the lower atmosphere. If the atmosphere were transparent to infrared radiation as it is to visible light, the Earth's average surface temperature would be about minus 18 degrees centigrade to 33 degrees centigrade colder than it is now. This phenomena is called the greenhouse effect because the atmosphere, loosely comparable to the glass of a greenhouse, transmits sunlight while trapping heat inside. The greenhouse effect is a natural atmospheric process that is necessary for life as we know it. However, too much greenhouse effect caused by burning of fossil fuels and deforestation may cause harmful environmental change. Much of the incoming solar energy is used to evaporate water. Every gram of evaporating water absorbs 580 calories of energy as it transforms from liquid to gas. Globally, water vapor contains a huge amount of stored energy known as latent heat. When water vapor condenses, returning from a gas to a liquid form, the 580 calories of heat energy are released. Imagine the sun shining on the Gulf of Mexico in the winter. Warm sunshine and plenty of water allow continuous evaporation that converts an immense amount of solar means light heat energy into latent heat stored in evaporated water. Now imagine a wind blowing the humid air north from the Gulf toward Canada. The air cools as it moves north, especially if it encounters cold air moving south. Cooling causes the water vapor to condense. Rain or snow falls as a consequence. It is not only water that has moved from the Gulf of Midwest. 580 calories of heat have also moved with every gram of moisture. The heat and water have moved from a place with strong incoming solar energy to a place with much less solar energy and much less water. The redistribution of heat and water around the globe are essential to life on Earth. Uneven heating with warm air close to the equator and colder at a high latitude also produce pressure difference that cause wind, rain, storm and everything else we know as weather. As the sun warms the earth's surface, the air nearest the surface warms and expands, becoming less dense than the air above it. The warm air must then rise above the denser air. Vertical convection currents result which circulate air from warm latitude to cool latitude and vice versa.